All right, so that's isotopes and how we see different versions and how we determine the number of particles in the nucleus. Now we have to talk about what's called relative atomic mass. Relative atomic mass, the atomic mass unit, is a constructed unit that we came up with to measure the mass of atoms. They took a carbon-12 atom, which is a pretty standard atom, and they did about 1/12 of it. So if there's 12 particles in the nucleus, okay, each proton and each neutron is going to be about 1. And that's what you see right here, okay? You see a proton is about 1.0007 whatever AMUs. Neutron is 1.0008665 AMUs. Mass of an electron is 0.005486 AMUs. Now you will notice I do not want you to memorize these numbers. The take-home message here is that protons and neutrons are about 1 on this whole AMU scale, and that electrons are about 1/1000th. Okay, so in other words, the protons and the neutrons make up most of the mass of the nucleus of an atom, and electrons are extremely, extremely tiny at about 1/1000th the size of those particles. So that's the take-home message on these. Don't memorize that. I'm not going to ask you unless you're bored and you have nothing else to do. Now, relative atomic masses, hydrogen is about 1.01 AMU, nitrogen is about 14.01, and you'll notice that the mass number of those substances are close, but they're not identical. And the reason that they're not identical is that the relative atomic mass does include electrons. And although they're small, they can have a little bit of an effect, hence the 0.01 out here. Okay, so that's going to have an effect. Plus, if you remember, the protons and the neutron masses aren't exactly 1 AMU either. So there's going to be that differences for those. Okay, the last concept we got to talk about is what's called average atomic mass. Average atomic mass is a weighted average, and people always get confused when we talk weighted averages. Of the weighted average of the atomic masses of the naturally occurring isotopes of each element. And you calculate this by multiplying each atomic mass by its percentage and then adding them up. Okay, if you've calculated weighted grades, you've done similar calculations to this. So let me show you a sample. Okay, we have two isotopes of copper, copper 63 and copper 65, and they're not a 50-50 split. Okay, copper 63 makes up 69% of the population, copper 65 makes up 30% of the population. In order to solve these problems, the average atomic mass of copper 63 is 62.929. So we need to multiply it by its percentage. And in order to do that, you're going to take the decimal place and move it over 2 places. So you're on your calculator, you're going to take 0.6915 and you're going to multiply it by 62.929. I'm going to carry extra significant figures here. So I'm going to put 43.515. It's a little bit tough to see. I apologize for that, but 43.515. Do the same thing with copper 65. I'm going to move the decimal place over. I'm going to take 0.3085. I'm going to multiply it by 64.927, and I'm going to get 20.029. And then I just add those up. Okay, when I add those up, I end up with 63.54, and I'm going to put AMU. Now I know you kind of only half heard me and you didn't really understand what was going on, but the fact that this is a weighted average. So this weighted average means that the weighted average represents the fact that there's more copper 63. Because if I had added these two up and gotten a traditional average, 62.929 plus 64.927, I add those up and divide by 2, my traditional average would have been 63.928. Okay, and that's not what it is. It's lower than that, and that simply reflects the fact that there's a higher percentage of this, so it kind of pulls the average its way. Same thing with our grades. We have weighted grades. Our test scores are 50% of your grade. So if you take a test, it's going to pull your grade down a lot more than just a quiz or a homework assignment. Okay, we're going to do lots of practice with these in class, so